Do 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 do. Last topics for grade 11 chemistry. We're going to look at dilution and dissociation, both talking about solutions. So dilution, the first thing, and you should have an idea of what a dilution is in your everyday life. It's just the process of decreasing the concentration of a solution by adding more solvent. So remember, the solvent is the liquid that is doing the dissolving. So if you put more liquid in and there's less of the stuff being dissolved, the solute, then it's going to be more dilute, or it's going to have a lower concentration. The common scientific practice is to begin with a concentrated solution and add solvent, usually water, to decrease the concentration to the desired level. So that's what we do in the lab when we get ready for you guys to do an experiment. We start off with a very concentrated solution and add some water to it until it is quite dilute. And then it's a bit safer for teenagers to use. So the formula for actually calculating these is like so. C1V1 equals C2V2, and C1 and V1, we already know what C and V are. Those are the concentration and volume before dilution. And unsurprisingly then, C2 and V2 are going to be your concentration and volume after dilution. So the product of your concentration and volume beforehand is equal to the concentration and volume product afterwards. And what do we know? That concentration times volume equals moles. So what we're saying is the moles of your solute before is really equal to the moles of your solute afterwards. But because you have a higher volume afterwards, you'd have a lower concentration. But we haven't actually changed the amount of moles of solute that's in there. We've just changed the amount of solvent. So let's look at an example of using this formula. So 1,300 milliliters is added to 200 milliliters of a 2.4 molar ammonia chlorine solution. What is the final concentration? So we have C1, we have V1, we have C2, and we have V2. So the concentration, C1, is your concentration before. It says it's a 2.4 molar solution. The volume is your V1 is your volume before. That was our 200.0 milliliters. We always like to work in liters, so let's divide that by 1,000. That gives me 0.2000 liters. Remember, keeping the number of significant digits. What is the final concentration? That's our C2. And our V2, well, that's our volume afterwards. Careful. A lot of people say V2 is 1,300 milliliters, but what is our actual volume? We're only adding that amount. We're adding 1,300 milliliters to the existing 200 milliliters. So how many do we have? Well, we have 1,500 milliliters, or 1.5 liters. And so you got to make sure some of these questions, they're going to tell you how much you add. Some will tell you the final volume. So just be careful reading these. So let's plug in our formula. C1V1 equals C2V2. If I want to solve for C2, I'm going to divide this side by V2 and this side by V2. So I'll have C2 equals C1V1 divided by V2. And just plugging stuff in here, we have 2.4 times 0.2000 divided by 1.5. And when I do that, what do I get? I get 0.32 molar solution. And we can just double check, does that make sense? This is a lower concentration than what we started off with, so that probably makes sense. I had 2 significant digits, so I have 2 significant digits here. Last topic is dissociation. So dissociation is just the separation of ions that occurs when an ionic compound dissolves in water. So what happens? We've already talked about solubility. We said if an ionic compound is highly soluble, when you put it in water, it breaks apart. And what that means is it's actually going to break apart into ions. So here's an example. A highly soluble ionic compound is NaCl, sodium chloride. So we would say that this is solid. You put it in water, and we've all done this. You put salt in water, and it dissolves. Well, when it dissolves, it dissociates. What that means is it breaks apart into sodium ions and chloride ions. So we have a dissociation equation that looks like this. Here's my sodium ion, and this is aqueous because it's in water, plus my chloride ion, which has a negative charge, and that's also aqueous. Now, this is the part that you might get confused about. This is not a decomposition reaction. A decomposition reaction of sodium chloride would look like this. We'd break it apart into sodium and chlorine's diatomic. We'd have to balance it by putting a 2 here and a 2 here. This is a decomposition reaction. This is not what we're talking about. When we are talking about a dissociation reaction, we're talking about putting it in a liquid and seeing it separate into its ions. So here we have a positive 1 sodium ion and a negative 1 chloride ion. We do still need to balance this, but in this case there is 1, 1, 1, and 1, so we're okay here. So please don't try to decompose these things and get something like this where you end up with a diatomic element. We're breaking them apart into their ions. So dissociation depends on solubility. We've talked about that before. So if you look at magnesium chloride, when you put magnesium chloride into water, you check your solubility table. It says chloride has high solubility with most and low solubility with 6 other ones. Magnesium is not in those 6 other ones. It's in the most. So this is soluble. So if it's soluble, it will break apart into its ions. So it will break apart into magnesium ion, which has a 2 positive charge, and this would be aqueous, plus a chloride ion, which has a negative charge, which will also be aqueous here. Now, we do have to balance. Like I said, we have 1 magnesium, 2 chloride, we need a 2 chloride over here. So we do have to balance, but you're only going to write the element with its charge, or the element with its charge. Something like calcium carbonate, if you take a look on your solubility table, this is not soluble. So it's not going to break apart into its ions. So in this case, we would just actually write does not dissociate. And we could even write because it's insoluble. It has low solubility. Here's one of these examples. This is sodium chloride put in water. So here it is being a solid before it's put in water. When it's put into water, what happens? It breaks apart into sodium ions and chloride ions, and they are going to be separated. Here's 2 more examples. Let's just take a look. Let's see if these would dissociate. And if they do, then let's write them. So calcium iodide. If you take a look at that, iodide has high solubility with most. So we're going to break this apart into calcium, which has a 2 positive ion. And we'll have iodine, which has a 1 negative, or sorry, iodide, I should say, which has a 1 negative. We need to balance, so we need a 2 here, and we're off to the races. Ammonium, excuse me, ammonium sulfate here. Again, we would look up sulfate, SO4. We would find that it's highly soluble with most, so it is going to break apart. It's going to break apart into ammonium, so that's NH4, and ammonium has a 1 positive charge. That's aqueous. And it will break apart into sulfate, which is SO4, with a 2 negative charge. And this will also be aqueous. So here we're talking about polyatomic ions rather than just monatomic ions like this, but it's the same thing. So now we got to balance. We have 2 ammonium. We need 2 ammonium here, 1 sulfate, away we go. The last... What this does tell us is that solutions that contain ions will conduct. We talked about conductivity before. Solutions without ions will not conduct. So this means not all ionic compounds will actually conduct. We had said before that ionic compounds do. Now we're saying not all of them actually will. So an example would be like lead bromide, PbBr2. If you look at the solubility of bromide, it says it's high solubility with most, but it has a low solubility with lead. Sorry, I should be saying lead too. So in this case, this does not dissociate. Does not dissociate. So it will not conduct. So you have to be careful that not all ionic compounds will actually conduct, despite what we said before. They will only conduct electricity in water if they dissociate. If they do not dissociate, they will not conduct. The last thing we can do is for the ones that do conduct, we can talk about the ones that do dissociate, we can talk about the concentration of ions. So here's an example. What are the concentrations of all ions in a 0.12 mole per liter or molar solution of barium hydroxide? So first off, we need to write our dissociation equation. So here's barium hydroxide. We put it into liquid. It will dissociate into barium, which has a 2 positive charge, aqueous. That should be a Q. And hydroxide, which has a negative charge and is aqueous. In order for this to be a balanced dissociation equation, we need 2 hydroxide. We have 2 hydroxide here. We're all good. So what this question is saying is we have an initial concentration of barium hydroxide of 0.12 mole per liter, or molar. How would we determine the concentration of these individual ions? Well, how have we been doing this before? We use the mole ratio. The mole ratio between this and this is a 1-to-1 mole ratio. So if the concentration of barium hydroxide was 0.12 mole per liter, this concentration would also be 0.12 mole per liter, because this is a 1-to-1 ratio. Oops, 1-to-1 ratio. What about the concentration of hydroxide? Well, what's the ratio now? If we go back to barium hydroxide, it's a 1-to-2 ratio. What does that mean? It means for every 1 mole of barium hydroxide, we'll have 2 moles of just hydroxide. So in this case, we have 0.12, so we're just going to double it because it's a 1-to-2. If it was a 1-to-3, we would triple it. If it was a 1-to-4, we would quadruple it, so on and so forth. So if we double it because it's a 1-to-2, this will be a concentration of 0.24 moles per liter. Whoops, mole per liter. So there we go. There would be my answers to this question. These would be the concentration of my ions.